Hello guys, welcome back to my channel Algorithm Avenue. In our previous video, we have seen about the backpropagation algorithm in detail intuition. Now, in this video, we'll be seeing the backpropagation algorithm code implementation. Okay, I have divided this video into two parts. The first part contains backpropagation algorithm for regression problem, and the second part contains backpropagation algorithm for classification problem. In this video, we'll be coding the entire backpropagation algorithm from scratch. Okay, now let's see the initial setup before the coding part. First, I have created a sample dataset which contains 4 rows of data and 2 input features and one output label, that is price. And I have also created a sample neural network which is 2-layer neural network which contains an hidden layer and one output layer, and which contains 2 hidden units in the hidden layer, and also contains two inputs, that is number of rooms and number of floors. Okay, now this is my algorithm. Okay, this is my backpropagation algorithm. This is my entire flow of backpropagation algorithm. Now initially I'm setting number of epochs. I'm setting number of epochs means for how many epochs my code should run. So initially I'm setting it as 7. Now my algorithm, what I do is I'll be running a for loop in the number of epochs. Okay, I'll be running a for loop in the number of epochs, and this for loop is written to run through the number of rows in our dataset. Okay, this main for loop runs through the number of epochs. This for loop, that is j for loop, runs through the number of rows in the dataset. Okay, now in this for loop, what I'll be doing is I'll be picking up a row. And give as input to the sample neural network. Okay, I'll be picking up a row and give as input to the sample neural network. Initially I'll be picking up my first of data, and I'll be giving it as input to my sample neural network. What happens here is, first this 3 and 5 goes as input to the sample neural network. Now they forward propagate. Okay, they forward propagate by multiplying the weights and bias values. Okay, multiplying with weights and adding the bias to it, they forward propagate, and some predicted output. Okay, some output is predicted. Now after prediction, what happens is you calculate the loss between the predicted output and true output. Okay, you calculate the loss between the predicted output and true output. That is, y hat is my predicted output and 2 is my true output. Now I'll be calculating the loss between y hat and 2. Okay, after calculating the loss, okay, the metric I'm using to calculate the losses, mean squared error loss function. Okay, mean squared error loss function. Now after calculating the loss, what I will be doing is I'll be backpropagating and update the weights and bias values. Means, how do I actually update this weights and bias values? Is with the help of gradient descent algorithm. I'll be updating my weights and bias values. Okay, now what is this gradient descent algorithm is? It is used to update the weights and bias values. Okay, the w new is equal to w old minus learning rate dou L by dou w old, and b new is equal to b old minus learning rate dou L by dou b old. Okay, this is the gradient descent algorithm. After this entire process is done, I'll be picking up the second row. Okay, I'll be picking up the second row and I'll repeat the entire process, and I'll be picking up the third row. I'll be repeating the entire process. I'll be picking up the fourth row, and I'll be repeating the entire process. After completion of the four rows, what happens is average loss is calculated for that epoch. Okay, for that epoch, first epoch is selected. After first epoch, you go through this for loop. It selects the first row of data, and this entire process is done, and losses. Okay, and some loss is calculated, let's say L1. After this you select the second row of data, and L2 loss is calculated, and you select the third row of data, L3 loss is calculated, and you select the fourth row of data, L4 loss is calculated. After calculating of this four losses, at the end of that epoch, you do an average of those losses, and you print the average loss. Okay, average loss for that epoch means, for 7 epochs, how many losses are being calculated? 7 losses are being calculated. Okay, this is the entire setup for coding our backpropagation algorithm from scratch. Now in the next part of the video, I'll be showing you the all the 9 derivative values. Yes, these are my 9 derivative values that I have already calculated in the previous video. If you have not watched the previous video, please go and watch the previous video. Okay, these are my 9 derivative values, and with the help of these 9 derivative values, what I'll be doing is I'll be writing the backpropagation algorithm from scratch. Okay, now let's move on to our desktop and see how we design our backpropagation algorithm.
Yes, in our previous section of the video, we have seen three things. The first is I have created a dummy dataset which contains 4 rows of data, 2 input features and 1 output label. Okay, now I have also created an sample neural network. The second thing is I have also created a sample neural network which contains 2 layers. The first is hidden layer and the second is output layer. Okay, the third thing is I have written the 9 derivative formulas that I have calculated in the previous video. Now in this section of the video, what we will be doing is we will be creating our backpropagation algorithm on our own with the help of those formulas. Okay, now let's start. First, I have imported the necessary libraries that will be required to implement my backpropagation algorithm. Okay, the first is import numpy as np. The second is import pandas as pd. Okay, these are my two libraries. And the second is I have created my dataset. Okay, I have just created my dataset over here, which contains two input features, that is rooms and floors, and my output label is y, that is price. Okay, these are the corresponding data values. Okay, now I'm printing my data, that is which contains two input features and one output variable, that is price, and this is my entire data. Okay, now in my next step what I am doing is initially I need to initialize my parameters. Okay, initialize my trainable parameters, that is weight values and bias values. Okay, in our model when we have calculated, I have got around 9 trainable parameters, right? I have got around 9 trainable parameters, among which 6 are weights and 3 are bias. Now I need to initialize those parameters with some values. Okay, now in this step I'm doing that. Okay, now this function what it is taking as input is, it is taking layer dimension as input. Okay, what actually this layer dimension specifies is, now this layer dimension specifies the shape of the neural network. Okay, the layer dimension specifies the shape of the neural network. Okay, what actually is the shape of the neural network is, now shape of the neural network is defined as inputs, hidden units and outputs. Okay, inputs, hidden units and outputs. Okay, now in our case, okay, with respect to our neural network, how many inputs do we have? We have two inputs, right? Okay, we have two inputs. The number of hidden units are 2 and number of output units are, okay, number of nodes in the output layer are 1. So our dimension becomes 2 comma 2 comma 1. Okay, now this function takes the input of the dimensions of the neural network and it determines the total number of parameters and it initializes some values to the trainable parameters. Okay, what actually it is initializing? It is initializing 0.1, okay, 0.1 to my weights and 0 value, okay, 0 value to my bias values. Okay, now I have 6 weight values. I have 6 weight values that are initialized with 0.1 and 3 bias that are initialized with 0 value. Okay, this is my entire function which is returning those parameters, which is returning those 9 trainable parameters. Okay, now I'm giving a input to that function and printing my trainable parameters. Okay, I'm giving my input dimension, hidden units and outputs, and these are my entire 9 trainable parameters. Okay, between input layer and hidden layer I will be having 4 weights, right? Those 4 weights are initialized with 0.1. Okay, now for the hidden layer I have 2 hidden units, right? Those hidden units are initialized with 0 bias. Okay, now between the hidden layer and output layer I have two weights, right? Those 2 weights are initialized with 0.1 value. Okay, now we corresponding to output layer I have one output node. That output node contains single bias. That single bias is initialized with 0 values. Okay, this entire function I have written to initialize my trainable parameters. Okay, total trainable parameters corresponding to our sample neural network. Yes, now I successfully initialized my trainable parameters. Now what next? I need to calculate the output of each node. Okay, Now I'll be having each node will be having some output, right? The output values are O11. Okay, in the hidden layer I'll be having two hidden units. Those two hidden units will be having some output. Those two outputs are O11, O12, and in the output layer I'll be having one output node. Okay, that output node is O21. So I'll be having three set of outputs, right? Three set of outputs. Now I need to calculate that output. Okay, I need to calculate that output. This is the function which calculates the output. Okay, this is the function which calculates the output, which take inputs as a previous, w weights, b bias. Okay, soon I'll be telling what's this a previous specifies. Okay, now this is the calculation, this is the output calculation, that is z is equal to weight transpose into x plus bias. Okay, weight transpose into x plus bias, where x is the input, w transpose is the weight matrix, b is the bias matrix. Okay, this is the entire calculation of the output of the node. Okay, this is the main forward propagation function. Okay, this is the main forward propagation function. First we'll be starting with the hidden layer, we'll be selecting an row, we'll be giving it as an input. Now that input will go through the neural network, and some outputs are calculated, and it will be reaching our output layer. Okay, it will be reaching our output layer. This is the main forward propagation function, which internally uses this linear forward method. Okay, this linear forward function. Okay, this is our main forward propagation function. This is the function to determine the output of the node. Okay, now what actually this main forward propagation calculates? Okay, this main forward propagation function takes input as x. Okay, takes input as x. This x specifies the inputs, the actual inputs that are given to our neural network. Parameters determine the weights and bias values. Okay, parameters determines the weights and bias values. Okay, now just I am printing those weights and bias values. Okay, our initialize weights and bias values. Let me comment this out. Yes, I have uncommented this. Now what actually this function returns? Is a and a previous. What are this a and a previous? A is nothing but our output, predicted output. A is nothing but our predicted output. Okay, A is nothing but our predicted output, which is nothing but O21. Okay, A is nothing but O21. A previous contains two values. Okay, A previous contains two values. Those are O11 and O12. Okay, A is our predicted output, that is O21, and A previous contains two output values that are from the hidden layer. Okay, that are from the hidden layer. Hidden layer contains two outputs, right? Hidden layer contains two outputs. Those two outputs are stored in A previous. Okay, now you may have a doubt that why are we actually returning this A previous values? Okay, in calculation of those partial derivatives, we have seen that the the use of O11 and O12. Okay, in calculation of those partial derivatives, we have seen the use of O11 and O12. So that is why this main forward propagation function is returning that previous calculated outputs. Okay, is returning that previous calculated outputs. That is A2. That is A2 is my O21, and A1 is nothing but O11 and O12. Okay, now what I am doing is I am writing a function. Okay, let me come over here. I am writing a function to update my parameters. Okay, I'm writing my in this piece of code. I'm writing a function to update my parameters. This is the function to update my parameters. Okay, now let's see what actually this function is doing. Okay, now this function takes, okay, this is the update parameters function. This function takes parameters y. Okay, parameters are nothing but trainable parameters, 9 weights and bias values. Y is nothing but true output. Y hat is nothing but predicted output. A1 is nothing but previous layers output. Okay, we have two hidden units, and corresponding to that we will be having two outputs, right? Those two outputs are stored in A1, and x is nothing but our input, okay, actual input of the data. Okay, it takes this this 5 parameters as input, and it is calculating something, right? It's calculating something. Okay, what's that something is w new is equal to w old minus learning rate dou l by dou w old. Okay, this entire formulation is nothing but weight updation formula. Okay, weights and bias updation formula I have written over here. Okay, now when you see this part, okay, let's focus on this part. This part is nothing but the partial derivative. Okay, this part is nothing but the partial derivative that I have written on the board. Okay, I have written on the board some 9 formulas, right? Among that, the first formula, that is 2 into y minus y hat into previous layers output. Okay, previous layers output. Okay, this is the formula, and this 0.0001 is the learning rate, and this is nothing but the old weight, and this is nothing but the new weight value. Okay, I'm entirely implementing weight updation formula over here. Okay, you can see that I have already written and comment, that is w new is equal to wl minus learning rate into the partial derivative value with respect to the weight. Okay, with respect to the weight. Okay, here I'm calculating the here I'm updating the bias value. Okay, here I'm updating the bias value, that is b new is equal to b old minus learning rate dou l by dou b. Okay, dou l by dou b. Okay, what's the bias that will be present over there? Okay, I'm setting my learning rate to 0.001. Okay, 0.001. Okay, you can see that in actual my weight updation formula, it's actually minus. Okay, now in my weight updation formula, it's actually minus, but when I written a code to update the weights and bias, I have actually written the plus. Okay, I have actually written the plus. Why? Because in the calculation of the partial derivatives, you see that initially you have minus beside the equation. Okay, beside the equation you have minus, right? Beside the partial derivative equation, you see that you have minus. Okay, that minus into this minus, okay, that minus into this minus has actually become plus over here. Okay, that is why I have written plus over the weight and bias updation formulas. Okay, this is my entire weights and bias update function. Okay, after defining my function, now what I will be doing is I'll be taking the first row of data and I'll be applying all the functions to it. Okay, I'll be taking the first row of data and I'll be applying all the functions to it, and I'll be calculating the predicted output and also the updated weights and bias parameters. Okay, yes, now what we'll be doing is we'll be taking the first row of data. Okay, what's the first row of data? It's 3 comma 5. Okay, 3 comma 5 is my first input features. Okay, first input numerics, and 2 is my output numeric. Okay, 3 comma 2 are my inputs and 2 is my true output. Okay, now let me send the inputs through these functions, and let me calculate the predicted output and also updated weights and bias values. Okay, this piece of code, I have written for implementing that. Okay, I have stored my input features to x, and my output true output. Okay, my output, that is true output, to y. Okay, my input features, that is 3 comma 5, are stored in x, and my output numeric is stored in y. Okay, these are my x and y values. Okay, now I have initialized my parameters to 2 comma 2 comma 1. Okay, not parameters but actually the shapes. Okay, actually I am giving the input to the initialize parameters function. Okay, where I have written it over here. I'm just giving the input dimensions of the layers. Okay, input dimensions of the layers, so that it can calculate the parameters. Okay, it can calculate the parameters, and I am storing those parameters in the parameters variable. Okay, I'm storing that in my parameters variable. Okay, after doing this step, I'll be printing my x and y values. Okay, what I'm checking out, what are actually my x and y values. Okay, these are my actual x and y values. This is 3 comma 5 is my x value and 2 is my y value. Okay, these are my inputs and outputs. Now after determining the inputs and outputs, now I need to send my first row of data to the neural network. Okay, first row of data through the neural network. So what I'll be doing, I'll be applying the forward propagation. After selecting the row, after selecting my first row, I'll be taking that entire first row and sending through the, I'll send it through the sample neural network, right? I'll be sending through a sample neural network. That is nothing but forward propagation. So I'm applying my forward propagation over here, which takes x. X is nothing but actual inputs as the arguments, and parameters, okay, parameters as my arguments. Okay, after taking this x inputs and parameters as my arguments, what actually it calculates the outputs of the nodes. Okay, it calculates the outputs of the each nodes. How does it actually calculate the outputs of the each nodes? W transpose into x plus bias. Okay, through this formula it calculates the outputs of the nodes. Now let us go through this function. What actually this function is returning? A and A previous, right? A and A previous means it is returning the three values. That is, A contains predicted output, A previous contains nodes outputs of the each node. Okay, now these returned values are stored in y hat and a1. Y hat contains this value of a, and a1 contains this a previous. Okay, a1 contains this a previous. That is nothing but o11 and o12. Now I'm printing that a y hat and a1. Okay, now when I print the values, you see that a naught. Okay, a naught is nothing but the output of the input layer. What's the output of the input layer? Okay, output of the input layer is nothing but what input we are actually giving. Okay, output of the input layer is nothing but what input actually we are giving to the input layer. The input that we are actually giving to the input layer is 3, 5. So it is specifying a naught is equal to 3, 5. Now we have 4 weights with respect to input layer and hidden layer, right? We have 4 inputs with respect to input layer and hidden layer. So those 4 weights are initialized with 0.1 values. And next, when it comes to hidden layer, it has 2 bias that are initialized with 0 value. And when it comes to A1 is nothing but the output of the nodes, the outputs of the 2 nodes in the hidden layer. So those values are calculated to be 0.8 and 0.8. Okay, now these two are my same calculated output values, and W2 is nothing but the weight values with respect to hidden layer and the output layer. Yes, this B2 you see, right? This B2 is nothing but the output layer node. This B2 is nothing but the bias of the output layer node, that is initialized with 0 value. This A2 is nothing but O21. A2 is nothing but O21, that is the predicted output of the model when first row of data is given as input. When the first row of data is given as input, A2 is the predicted output. A2 is nothing but O21 with respect to the terminology, with respect to the notation. 0.16 is nothing but O21. Okay, this is the predicted output. Now I'm just printing the predicted outputs of the each node. Okay, this is with respect to the output layer node, that is predicted as 0.16, and these two predictions are nothing but the predictions of the hidden layer nodes. Okay, my first hidden node is my first hidden unit is giving me as output as 0.8, and the second hidden unit is giving as output as 0.8. Okay, these are my weights and bias values and corresponding outputs of the each nodes. Now after calculating the predicted output according to our algorithm, what are we actually doing? After calculating the predicted output, we are determining the loss. Okay, now the loss function that we are using is mean squared error loss function. The loss function we are using is mean squared error loss function, that is y minus y hat whole square. I already have y in my data. Y hat is nothing but 0.16 and it is squared. Okay, and my loss is coming out to be 3.3856. okay, this is my loss when my first row is given as input. Okay, when my first row is given as input, this is the corresponding loss that my functions have calculated. Okay, that my functions have calculated. Okay, now this is my y hat value. My y hat value is in the form of array, so I'm storing this y hat value in the form of numeric over here. Okay, this y hat value is actually an array, so instead of array I'm storing it as an item. Okay, I'm storing it as an item, that is single numeric. Okay, that is 0.16 something value. Okay, now these are my a1 values, that is the outputs of the previous nodes. Okay, now I'm calling my update parameters function. Okay, I'm calling my update parameters function. Now I'm running this parameters function. Now these are my entirely calculated parameter values. Okay, these are my entirely calculated parameter values. Now how the flow happened is, first first I'm giving the first row as input. It is forward propagating, and after forward propagation it is calculating the y hat predicted output. After calculation of y hat predicted output, I am determining the loss between predicted output and true output. After determining the loss, to reduce the loss, I am backward propagating. In this step. Okay, I'm backward propagating and updating my trainable parameters in this step. Okay, updating my trainable parameters in this step. After my first updation, my weights and bias parameters are determined to be 0.10 something numerical values. These are my 4 weights corresponding to input layer and hidden layer. These are my 2 bias corresponding to the hidden layer. These are my 2 weight values corresponding to the hidden layer and output layer, and this is my only single bias value in the output layer. Okay, these are my entirely updated weights and bias parameters after sending the first row as input. Okay, first row of our data as input. Okay, yes, I have successfully updated the trainable parameters for the first row of data. Now what I will be doing is, I'll be doing the similar thing for the second row of data as well. Now I'll be taking my second row of data, I'm picking my second row of data, and again I am applying the same functions on my second row of data. Okay, I'm taking the second row of data and applying the same functions. Okay, same functions that I previously applied it on the second row of data as well. Now when I apply the same functions to the second row of data, the parameters that are calculated to be 0.103555, and these are the numerical weights and bias parameters that are calculated after passing my second row of data. Okay, these are the weights and bias parameters. You can see that there is a difference between the weights and bias parameters before sending the second row of data and after sending the second row of data. Okay, you see a slight change between the trainable parameters. Now we'll be sending the third row of data similarly. Okay, third row of data similarly. Yes, I have seen the third row of data and I have applied the same functions to the third row of data as well, and these are the updated trainable parameters. You can also see the change between these two. Okay, these two, you can see the change between these two trainable parameters. They are slightly updated, right? They are slightly updated. Now I have individually calculated the trainable parameters for each row of data. Now instead of doing that for the individual rows, now what I am doing is I'm writing a loop which takes the rows, individual rows, and which applies all the functions to it and which prints the average loss. Okay, now let me write the loop. Okay, now let me write the loop. Okay, now first I have initialize the parameters. I have given the input to the initialize parameters function, that is 2, 2, 1, my neural network dimensions. Okay, now I'm storing that returned parameters in the parameters object. Okay, I have set the epochs to 7. Now I'm running a loop. I'm running a loop in the epochs. Now I'm running a loop in the epochs and also creating the list. Okay, I'll be telling you why actually I'm creating this loss list. Okay, in the further I'll be telling you that. Now I'm writing this j loop to run through the rows of the data, to run through the rows of the data. First it picks the first row. After appending that, it picks the second row of data, and picks the third row of data, and picks the fourth row of data, and next it comes to the second epoch. Okay, in that way I'm writing two for loops, which first for loop runs through the epochs, the second for loop runs through the data. Okay, now I'm picking the data over here. Now I'm applying the same functions over here. I'm calculating the y hat over here. Now I'm applying the update parameters function. Now I'm appending the loss. Okay, why actually I'm appending the loss to this list is why I'm appending the loss to this list is, after the end of each epoch, now when I send the first row of data, I'll be getting the loss. Okay, in an epoch we'll be updating our parameters 4 times. Okay, so we'll be printing the 4 losses in just a single epoch, right? We'll be updating the parameters 4 times in an epoch. So I'll be printing the 4 losses. Okay, I'll be printing the 4 losses in a single epoch. So to avoid that, what I am doing is I'm calculating the mean loss for the 4 rows of data. Okay, I'm calculating the mean loss over here to the 4 rows of data. Means you see that internally I'm applying stochastic gradient descent. Okay, internally I'm applying stochastic gradient descent. What stochastic gradient descent specifies? The stochastic gradient descent picks the single row of data, it calculates it updates the parameters for each single row of data. Okay, it picks the single row of data, it updates the parameters for single row of data, and at the end of the epoch it calculates the average loss, right? It calculates the average loss. Same I'm doing it in my for loop. I'm internally applying stochastic gradient descent. Now how actually this works is, first I'm picking the first row of data, it calculates the loss, it appends to the list. Second it picks the second row of data, it calculates the loss and appends to the list. Third loss, fourth loss. Now I have 4 losses. Now for that 4 loss values, I am calculating the mean value, which determines the average loss of that epoch value. Yes, I hope you have got that, how we are internally applying the stochastic gradient descent in this for loop, right? I'm just for an epoch I'm printing just a single loss. I'm updating my trainable parameters 4 times in a single epoch, but I'm printing the loss single time, that is average loss per epoch. I'm printing the average loss per an epoch. Okay, now just I have run the code. After running the code, wait, just let me comment this out. Yeah, I'm printing all the A0 and A1 values. Wait, yes, I'll be commenting this. When I comment this, it does not print the unnecessary values. Okay, just a second. Yes, I have commented this out, and let me run the code. Yeah, now let me run the code. You see that per single epoch it's printing a single loss. Okay, it's printing a single loss. You see that for the first epoch the loss is to be 30.33, and when it comes to 7 epochs, it has reduced to 1.408. Means your function is successfully implementing the backpropagation algorithm to reduce the loss. Okay, to minimize the loss, it's successfully implementing the backpropagation algorithm. When you train for more epochs, your loss will be much reduced. Okay, your loss will be much reduced. So we have successfully created our backpropagation algorithm. Okay, our own backpropagation algorithm to our corresponding dataset and sample neural network. Okay, these are the loss values. Okay, these are the loss values. These are the entire optimized weights and bias values. We have started our weights from 0.1 and we have improved our weights and bias values. Okay, you see that we have improved our weights and bias values. Okay, these are the optimized weights and bias values. Okay, now in the next section of the video, what we will be doing is we will be implementing the PyTorch implementation of backpropagation algorithm, and we'll be comparing the difference between, and we'll be comparing the our own backpropagation algorithm results and PyTorch implementation of the backpropagation algorithm results. Yes, now let's start with the PyTorch implementation of the backpropagation algorithm. Okay, now first initially I'm importing the necessary libraries, that is import torch. When you work on PyTorch, you need to definitely import the torch library. Okay, you need to definitely import the torch library. Import torch, import pandas as pd. Have successfully imported my necessary libraries. Now I have already have the dataset over, right? Okay, I have already dataset over there. What I am doing is I am just giving the input features. I am just giving the input features to X and output labels to Y. Okay, so you see that I'm just doing that over here. Okay, to X I'm giving the input features, to Y I'm giving the output labels. Okay, in this step I'm doing that. Yes, after doing this step, what I will be doing is I'm importing my necessary libraries to create the model. To create the model, I'm importing my necessary libraries, and this is my model. Okay, this is my model. This is my model, that is the sample neural network that we have seen. Okay, similarly I'm creating it over here, which is taking as input features, hidden units, and output features as my arguments. I'll be defining that input features, hidden units, and output features later. And this this model is having two layers with linear activation function. Linear activation function means there is no activation function applied to our model, applied to our model's output. Okay, I'm defining my two layers over here, and you see that this piece of code I have written to initialize my weights and bias parameters. Okay, why I have written this code is PyTorch internally what it does is it applies random weights and bias values, to our weights and bias. Right now, actually what we have created in our model, okay, in our model that we have created, the weights values are to be 0.1 and bias values are 0, right? But the PyTorch internal implementation is implementing some random values to weights and bias values. So what I am doing is I am modifying those weights and bias values. Okay, I am modifying those weights and bias values to 0.1 and 0. Okay, this piece of code I have written to modify the weights and bias values from random initialization to initialization of 0.1 and 0. Okay, now this is the forward propagation. This is our forward method, means how the input should flow through the neural network. First it must flow through the layer 1, second it must flow through the layer 2. Okay, this is our forward method. Now I'm creating an class instance over here, that is model 0, and I'm defining my features over here. Okay, input features to be 2, hidden units to be 2, and output features to be 1. Okay, these are my neural network dimensions. Okay, these are my neural network dimensions, that is 2 comma 2 comma 1. Okay, as it's a linear regression problem, I'm implementing MSE loss function. Okay, mean squared error loss function, and optimizer to be stochastic gradient descent. Okay, previously I have indirectly implemented in our previous for loop, I have indirectly implemented the stochastic gradient descent, but when it comes to our PyTorch implementation, it has already the stochastic gradient descent built in. So just I am calling that optimizer, that is stochastic gradient descent, and setting my learning rate to 0.001, and I am printing the model weights and bias values. The model weights are 0.1, model bias are 0, model weights between the hidden layer and output layer is 0.1, and model bias with respect to the output layer is 0. Okay, these are my initialized weights and bias values. Yes, we have successfully created our model and also initialized the parameters from random initialization to 0.1 and 0. Now what we will be doing is we'll be building our for loop, that is training loop, to backward propagation. Okay, first I have set my epochs to be 7, and I am running the for loop through the epochs, and I have also created an empty list of laws, and I'm setting my for loop to be trainable. Okay, I'm setting my for loop to training. Okay, entire training. Now I'm calculating the bipred values. I'm sending the x as input. Okay, x, that is input features to directly into the model, and calculating the bipred values. Now I'm defining my loss. Loss is equal to loss function. I have already created my loss function over here. It is taking the inputs as bipreds and y, and it is calculating the mean square error loss between the loss function. Okay, mean square error between the bipreds and y. Okay, after that I'm backward propagating, that is I'm applying the backward propagation. Then I'm applying my optimizer, that is stochastic gradient descent. After calculating the loss, I'm appending it to the list. Okay, I'm appending it to the list. For each row I'll be getting a loss. After completion of the epoch, after completion of a single epoch, I'll be determining the average loss of those 4 loss values. Okay, I'm just doing that over here. I'm printing the epoch and also printing the average loss per epoch, and also printing the optimized weights and bias values. You see that for 7 epochs my loss is reduced to 24 from 32. Okay, from 32 it has reduced to 24, and these are my optimum weights and bias values for 7 epochs. For 7 epochs, these are my optimum weights and bias values. These are the corresponding reduced loss values. You see that there's a major difference between the backpropagation algorithm that we have created and backpropagation algorithm that PyTorch is internally implementing. So the difference that it has created is because with due to the optimizer there is a major difference created over here. Okay, this is why there's a major difference between the our backpropagation algorithm and PyTorch internally applied backpropagation algorithm. Now you have successfully completed the linear regression. We have successfully applied the backpropagation for linear regression problem. In the next section of the video, what we will be doing is we'll be taking a classification dataset and we'll be applying the backpropagation algorithm to our classification dataset. Okay.
In our previous part of the video, we have successfully built the code from scratch for backpropagation algorithm with respect to regression problem statement. Now, in this part of the video, we'll be building the code from scratch for backpropagation with respect to classification problem statement. Okay, the necessary changes I have made is the first change I have made is with respect to dataset. Okay, I have taken the classification dataset this time, which contain paint and brick as my input features, where these are the ratings of the paints and bricks quality and the strength of the house. Means 1 means it is a strengthy house and 0 means it is a weak house. Okay, this is my classification dataset, and this is my sample neural network. Okay, this is my sample neural network which contains two input variables and two hidden units in the hidden layer and one output unit in the output layer. Now the only change I have made in this neural network is I have changed the activation function from linear activation function to sigmoid activation function. Previously in my neural network, for each node I have applied linear activation function. Okay, but in this case of classification problem, I have applied sigmoid activation function to each of my node. Means when I apply sigmoid activation function to each of my node, what happens is after the calculation of x into w transpose plus b, it goes into sigmoid activation function. Okay, after calculation of x into w transpose plus b, it goes into sigmoid activation function. Okay, now that value is stored in the z. Now the z value moves to the sigmoid activation function, where sigmoid activation function formula is 1 by 1 plus e to the power of minus z. Okay, that scales the output of each node between 0 to 1. Okay, this is the necessary change I have made in my neural network with respect to classification problem statement. Okay, I have applied sigmoid activation function to all my three nodes. Okay, the third change I have made is with respect to loss function. Okay, the third change I have made is with respect to loss function, where I changed my loss function from mean squared error loss function to binary cross entropy loss function. Okay, where minus y log y hat minus 1 minus y log 1 minus y hat is my binary cross entropy formula. Okay, now what we will be doing is we have determined all the 9 derivative with respect to regression problem statement in our previous video. Okay, now what we will be doing in this part of the video is later we'll be building the code, but initially we need to calculate all the 9 derivative values. But I will not be calculating all the 9 derivative values. I'll be showing you how to calculate a single derivative value. With respect to that, you can determine all the 9 derivative values. Okay, now let's move on with the first derivative value calculation. Okay, this is my sample neural network. This is my y hat predicted output. This y hat predicted output is sent. Okay, sorry, this y hat predicted output is calculated by sending the output of this node into sigmoid activation function. Okay, that is the thing you must remember. Okay, now let's start the calculation of the derivative. Now first, initially we take loss. Okay, initially, why do we update the trainable parameters? To minimize the loss. Okay, now how can loss be minimized? The loss can be minimized by changing the y hat value. How can we change the y hat value? We can change the y hat value by changing the value of z. Okay, we can change the y hat value by changing the value of z. Now, how can my z be changed? By changing this trainable parameters, right? By changing this trainable parameters. I'm calculating with respect to W211 weight, so I have considered W211 in my calculation. Okay, now let me calculate for dou L by dou W211. Okay, now dou L by dou W211 is equal to I'm writing this relationship as the product of direct relationships. Okay, product of all the 3 direct relationships. Okay, now dou L by dou y hat multiplied by dou y hat by dou z multiplied by dou z by dou W211. Okay, this is my multiplication of all the 3 direct relationships. Now when you multiply all these 3 derivative values, you'll be directly getting this value. Okay, now we'll be calculating this individual derivative values. Now first let me calculate this derivative value. Dou L by dou y hat is equal to, what is my loss function? My loss function is this. Okay, this is the loss function equation. Now when I find the derivative with respect to this loss function, y hat minus y log of y hat minus of 1 minus y log of 1 minus y hat. Okay, let me rub this. Yes, now let me find the derivative with respect to this loss function equation. Now when I find the derivative of log x with respect to x is 1 by x, so same applies over here. Okay, same derivative applies over here. So this comes out to be minus y divided by y hat minus 1 minus y is my constant. 1 minus y is my constant. So because I'm calculating the derivative with respect to y hat, so divided by 1 minus y hat. Okay, this comes out to be plus because internally I'm calculating the y hat derivative value as well. Minus y hat derivative is minus 1, so minus 1 gets multiplied and comes out to be plus. Now what I'll be doing is I'll be writing this fractions as a single fraction. Okay, individual fractions as a single fraction. That comes out to be minus y 1 minus y hat. Okay, even you can calculate as well parallelly. Divided by y hat into 1 minus y hat. Yes. Okay, now we'll be multiplying this values inner. Okay, this will be multiplying this values inside the brackets. Okay, inside the brackets. Now this comes out to be, let me write it over here, minus y plus y hat plus y hat minus y hat y. Okay, divided by y hat of 1 minus y hat. Okay, I'll be cancelling this out. The leftover part is minus of y minus y hat divided by y hat into 1 minus y hat. Okay, this is the derivative of dou L by dou hat. We have successfully calculated the derivative of this value. Okay, in the next part of the video we'll be calculating the rest 2 derivative values, and I'll also be writing all the derivative values in a place. Yes, in the process of calculation of the derivatives, we have successfully determined the derivative value of dou L by dou y hat. Now let us determine the values of these 2 derivative values. Okay, first This is my derivative value. Now let us determine dou y by dou y hat, dou y hat by dou z. Okay, dou y hat by dou z. Now what is the value of y hat? The y hat value is nothing but z when it's sent to sigmoid activation function. The output of that sigmoid activation function is nothing but y hat. Means z when it is sent to sigmoid activation function, it is giving us value of y hat. Means y hat is nothing but sigmoid of z. Means indirectly you are finding the derivative of sigmoid of z. Means indirectly you are calculating the derivative of partial derivative of sigmoid of z with respect to z. The sigmoid derivative is sigmoid of z into 1 minus sigmoid of z. Okay, the partial derivative value of sigmoid activation function is sigmoid of z into 1 minus sigmoid of z. Okay, now this sigmoid of z is nothing but y hat value. Now this can be replaced by y hat into 1 minus y hat. Okay, now we have successfully calculated our second derivative value. Now let us calculate our third derivative value, that is dou z by dou w211. Now before calculating the derivative value, we need to know what is the value of z. Okay, the value of z comes from the neural network. Okay, I hope you have already drawn the neural network. So with respect to that neural network, I am writing my z value. Okay, I am writing my z equation. Okay, that comes out to be O11 multiplied by weight W211 plus O12 multiplied by weight V12 plus bias, that is B21. Okay, that is B21. Now we need to find the derivative with respect to W211 of this z value. Okay, now the derivative value comes out to be dou z by dou W211 is equal to, when I find the partial derivative of this equation, this value becomes 0, this value becomes 0. Now I'll be left out with this value. The derivative of 2x with respect to x is 2, right? So similarly, we'll be writing O11 as my output of this derivative value. Okay, the output of this derivative is O11. Now let us multiply all the three derivative values and find out this final derivative value. Okay, now dou L by dou W211 is equal to multiplication of this three derivative values. Minus minus of y minus y hat divided by y hat of 1 minus y hat multiplied by this derivative value, again multiplied by O11. Okay, now you can see that these two terms cancel out. Okay, I'll be left out with minus of y minus y hat into O11. Okay, this is our final derivative value of this partial derivative. Okay, of this partial derivative value. Okay, this is my final derivative. Okay, now similar to this we have 8 more derivative values. I hope you can calculate the rest 8 derivative values, because the length of the video becomes very much lengthy. So this is my first derivative calculation. In our next section of the video, I'll be writing out the rest 8 derivative values. Okay, the rest 8 partial derivative values. By basing on that, you can calculate the other 8 partial derivative values. Okay. Yes, these are my all 9 derivative values. I have initially calculated the derivative value of this. Now these are the rest out 8 derivative values. Okay, there may be some mistakes, but you can resolve it by calculation by yourself. Okay, these are my left out 9 derivative values. These are my 9 derivative values. Now basing on this 9 derivative values, I will be writing the code for backpropagation algorithm on regression problem. Okay, basing on these equations, I'll be writing the backpropagation algorithm from scratch on classification problem statement. Okay, now let's move on to our desktop screen.
Yes, in the previous section of the video, we have successfully applied backpropagation algorithm to our linear regression problem. Now, what we will be doing is, we'll be applying backpropagation algorithm to our classification dataset. Okay, in our previous section of the video, you have seen that the dataset, the sample dataset, and the neural network, and also the derivative values, right? The 9 derivative values. Now we'll be entirely formulating them into the code. Okay, this is the data that this is the data frame. Okay, this is the data that I'm creating it over here, which contains paint and brick as my input features and strength as my output label. Okay, now this I'm printing the dataset. Okay, I'm just printing the dataset over here. Okay, let me run this. Yes, this is my entire dataset. Okay, which contains 4 rows of data, 2 input features and 1 output variable, that is strength. Okay, this is the same initialize parameters function that we have used in the linear regression problem. Okay, same, entirely same initialize parameters function. Okay, now this is my sigmoid for activation function. You see that the major difference between the regression problem and classification problem is, in case of classification problem, each node, the output of each node is applied to the activation function. Output of the each node, that is the value of z, the value of z is sent through the activation function, which scales in between 0 to 1. The sigmoid activation function formula is 1 by 1 plus e to the power minus z. So the output of each node is scaled between 0 to 1. Okay, this is the sigmoid activation function. After defining the sigmoid activation function, I'm creating the forward linear forward function. Okay, linear forward function, which helps in determining the output of the each node. You see that the major difference is I'm applying the activation function to my output of the node. Okay, this is a major difference between regression and classification problem. After that, same forward method. Okay, forward propagation, this is the entire forward propagation, and weights and bias updation formulas, these are the entire weights and bias updation formulas. I'm changing my learning rate to 0.0001, and these are the entire formulas. Okay, from here these are the entire formulas that I have calculated in the previous section of the video. Okay, now I'm writing the for loop. I'm writing a for loop to update the trainable parameters and also calculate the average loss for an epoch. Now I have initialized my parameters. Okay, the dimensions to 2, 2, 1, so that it can initialize the parameters to 0.1 and 0 initially. So I'm storing that in parameters, and I'm running it for 50 epochs, and I'm running a for loop in the epochs. And also I created the empty list of loss. I'm running an j loop through the rows of the data. Now I'm sending the different rows of data so that they can forward propagate, and loss is being calculated, and after calculation of the y hat, the loss is calculated. After determining the loss, the weights and bias parameters gets updated. After updating the weights and bias parameters, the second row of data comes into picture. Okay, the second row of data. After passing the second row of data, similarly third row of data and fourth row of data. So after the completion of the fourth row of data, one epoch gets completed. Okay, now I'm appending the loss. To the list. Okay, after completion of the first row, we'll be getting a loss rate. That loss I'm appending to the list. After completion of the second row, I'll be getting a loss that I'm appending to the list. After completion of the third row and fourth row, I'll get in 2 losses that I'm appending to the list. After completion of the 4 rows, I'll be calculating the mean loss. For an epoch. Okay, now when I run it for around 50 epochs, I'm getting the loss to be 0.69. Okay, I don't know why it's giving me the constant loss of 0.69. I think due to the less data, due to the availability of less data, it's giving me this value. Okay, this is the loss after the 50 epochs, and these are the optimum weights and bias values after the 50 epochs. You see that there is a major change from 0.1 to 0.09, and bias value from 0 to minus 5.2. Okay, yes. Now let us see how actually PyTorch implements the backpropagation algorithm on the classification dataset. Okay, similar to the previous section, I'm importing the necessary libraries. I'm storing the input features to X and output features to output labels to Y, and I'm creating the class over here. I'm creating the class to define my neural network. So the major change that I have made is for each node. Okay, for each node I am choosing an activation function as sigmoid activation function. For the layer 1, we'll be having the same sigmoid activation function. For the layer 2, we'll be having the same sigmoid activation function. That's a major change I have done over here. For the regression problem, we use linear activation function. For the classification, we are using the sigmoid activation function. That's the major change I have done over here. I am initializing the weights and bias parameters and forward method for the forward propagation, and I'm initializing the model to be model 0, and loss function is equal to BCE loss. The another change from the regression problem to classification problem is, in regression problem I have used MSE loss, mean squared error loss function. Here I am using binary cross entropy loss function. Okay, for classification, generally for binary classification we use BCE loss. Okay, binary cross entropy loss function. Okay, this is the optimizer, that is the stochastic gradient descent. I'm printing the model parameters, that is 0.1 for the weights, and for bias I'm giving initializing it to 0. Okay, now I'm writing a training loop. Okay, this is the entire training loop. I have set to 50 epochs. I'm running a loop for in the epochs. I created an empty list of loss. I'm setting the model to be training mode. I'm calculating the while logits over here. Okay, why I'm calculating the while logits is, when I send the x as an input, okay, x as an input to the model, what actually it does is, it gives me some predicted value, right? It gives me some predicted value. That predicted value will be out of range from 0.2 0 to 1. Okay, actually in our true output, when you see our true output is either 0 or 1. Okay, it's either 0 or 1, but it is not out of range of 0, out of range of 0 or out of range of 1. But when you calculate the y logits value, it may be 2.3, 3.3, 5.5, something. Okay, out of range from 0 to 1. So what I am doing is, I am calculating y logits, and I'm applying sigmoid activation function to the y logits. Okay, I'm applying sigmoid activation function to the y logits, so that I can scale the predicted output from 0 to 1. Okay, after calculating that, I'm storing it in the ypreds, and I'm calculating the loss between ypreds and true output. I'm doing the backward propagation, and I'm appending the loss to the list, and I'm printing the epoch and mean loss of the mean loss of the epoch. Okay, you see that for each epoch I have gotten something some loss, but the loss is being constant over here. There's a minimal change in the loss, that is due to the less data availability. Okay, the less data availability, you see, and some slight difference between the loss values. Okay, this is the average loss, and these are corresponding epochs, and these are the updated weights and bias values from 0.1 to 0.09 something, and 0.10 some numerical values. Okay, the bias is being updated to 0 to some minus 4.0004. Some bias values are being updated as well. Okay, these are the optimum weights and bias values, and these are the average losses for epochs. Okay, this is the entire back propagation algorithm code implementation. We have successfully implemented the back propagation algorithm on regression problem and classification problem, and we have also seen the difference. We have also compared the results of our own back propagation algorithm and PyTorch implementation of the back propagation algorithm. Okay, this is the entire video on the back propagation algorithm. If you like the video, please like, share and subscribe. Okay,